next Monday, so we shall have the NC session. So you go to the meeting room on the level 5 practice your NC. Okay, so today we're going to study about the beam. Okay. And before that, then I will announce another is add on to the okay, I think many of you did not do question 5 well. So I will post the question 4 and 5 again. So that you can do the solving. Okay. So please do I'll put down this. So for question 5 of your examination, you give your add up bonus of 10 marks. Okay. So you can solve that question. Okay. So that's the question 5. Okay. And then now we come to the beam element. Okay, and then another question to ask you is, so far I encountered, I've done some preliminary marking, so I find some of you still cannot solve these simultaneous equations. Please go back and try this lecture example, okay, solve by hand, okay. So it's important because otherwise, as we proceed, then you find it more difficult to solve the problem because the degree of freedom we are going to handle is more. And even some of you still did not do the matrix method. Okay, don't take this subject as the mechanics of material subject. Okay, you are not solving a very simple problem. You are going to solve a combination of truss element, later beam element. So please try to formulate the problem in the matrix form. Okay? So this is the take-home message. Okay? And then, again, during the solution, please work out the free body force. Okay, what is the thermal expansion? What is the thermal induced force? Draw them out on your this element drawing. Okay, don't leave it into your question sheet. You have to write on your answer sheet. Your answer sheet got plenty of places. Okay. 那你们同学作答的时候，不要给我最终答案。OK。你如果没有步骤，就给我最终答案。老师就会纳闷，你是偷看邻桌的同学的，还是这个超乎想象？答案是有原因出来的。你要把那个步骤都写齐。OK， 不要跳那个步骤。So these are some remarks. When you go back to do question 5, okay, please do the right way. Don't leave it. Keep all the intermediate steps. Don't leave them out. Okay. 好，那我们现在就开始上课。我先把这个录影片丢上去。我们今天就开始上这个2堂课。 What did you learn previously was these thrust and element. Okay, one of the big difference between the thrust and the beam is thrusts are actually two-ended questions. Let's see. Okay, anyway, I'll try from here. See the projections are working. So let's see. Okay. Wait a second. The projections. Let's see. Okay. So a thrust is a network of bar that only experience tension or compression. This is less possible because the bar are connected to each other using only the hinge. On the other hand, beam is a structure to resist the bending. So it differs from the thrust in that the thrust can resist moment, and the connections, at the connection there are actually kind of like fuses. Okay. So one of the examples that you can see, one of the beam structure are the bicycle frame. Okay, bicycle frame not just need to resist the bending. Okay, they also have to support the axial loading. So in this case, we're going to combine beam together with the truss to model a frame. Okay, so in the second NC session, we are going to design a model. We are going to build a model to predict the deformation of the bicycle frame. Okay. Another example of the beam bending test can be seen from the ground testing of the F-10 frame. Let's watch a video in the ground vibration test of the aircraft is beam bended. Okay, let's see. So this is a video showing the cantilever wing being tested. So okay. Hold it up. Okay. Okay, where's the sound? You see, they got the sound adjustment. Okay, let's see this. Okay, wait a second. I try to reset again. bending of the wing.
This is the house of the very first HV-50 aircraft ever built. In fact, this is more a prison since we will torture it a lot of times, in particular before the first flight. We have in front of us more than 2,500 tons of steel. This is the cage of the bird that we have in front of us. What is planned in this test campaign is to load the specimen mechanically and also to pressurize it. We will go to the extremes to check the structural behavior of the bird. When we will load it, so we will pull upward the wing, pull downward, pull the fuselage. In all the critical situations, we have installed 12,000 sensors on the specimen. So you can imagine between the offloading position of the wing, when we compensate simply the weight of the bird, and the max level of load, we have more than 5.2 meters displacement. So let's dive into the installation. The red pipes here are inlets where we are pressurizing the fuselage. So we have dummy windows, we have installed that, and the big pipes are connected to a music instrument that we call clarinet. Not to play music really, but just to pressurize and to torture the aircraft. Just imagine the aircraft will be pressurized in a worse manner than if it would be in space. More than 1.3 bars. It's like a bomb. If ever the cargo door is opening, we can damage the complete building up to the accidental effect. We are preparing the very last loading case that we plan to perform before the first flight. So it's really the result of 5 years efforts of the team, and the day of the first flight will be the communion and the celebration. My little contribution will be the opening of the flight envelope for the structural part.
Next, we shall see why this kind of beam bending is critical. Okay, let's see why beam bending is critical. We shall watch the video of this afternoon. Let's see. In the sky, how strong the wing need to be for aeroplane? Okay, so you can watch the one or two of the structure. So okay, so because in the sky, the airplane wing, even though it looks like cantilever, but they will be interacting with the air. Okay. Air will form vortices, and then the vortex will go up and down. This happens to be the same to bridge plate. So the bridge is actually kind of like a structure, but the root surface of the bridge could be excited into bending, and that bending can happen quite differently. Let's have a watch about the bending of the bridge. Okay, in an exaggerated way. So this is the one kind of a beam bending of the bridge. Okay. This is still a build-up structure. It's not a single beam. Okay. You can see also the torsion. Okay, the torsion of the bridge. And then next we'll come to see the bending of the aircraft structure when induced by the air. So the first example will be the bridge one, and then later you see the aircraft structure bending. We're going to have the sound. Yes. action happens on the top and the bottom surface, the beam will be twisted and even bent. So let's see the example of the glider. One of the glider actually is kind of like rubber with the So with this, now we know it is important to understand the vibration of the beam bending. Okay. But to start forth, we are not going directly to the vibration. We start with the static deformation. Okay. So how to model airfoil? Okay, you can model it in a 3D form. It's made out of trusses. It's made out of the skin. So ideally, you can model all the detail. But it is also possible to model the wing as a simple cantilever to give you a first estimation. Okay? So for beam element, you can break them down into many elements in series. Okay? This is still a cantilever, even though you have broke it down into a series connection of beam element. However, if you are breaking this into truss, so this is not a structure. 所以我们在讲这个连杆结构的时候，跟梁结构很大的差别是什么？连杆你如果是单根连杆，你支撑它，感觉好像不太稳，通常要3根连杆 ，OK。但是你如果是梁结构就不一样，你一根梁就是一根结构。你如果把它换成连杆，2节叫双节棍，3节那太多节，它不是结构。但是梁的话不一样，梁的话你虽然在分析的时候你把它分段，1段、2段、3段、4段，它还是悬臂梁。Okay, so this is a big difference. So when we found this kind of beam element elsewhere, you can also found them on the bimetallic coil. A coil is also a cantilever. So take for example, this is a bimetallic coil. You have a coil made out of 2 layers bonded together. The 2 layers are copper and iron strip. They are bonded together. When you do the heating up, then because of the difference in the thermal expansions, then you're going to have the unbending. Okay, this kind of unbending is also okay. So another form of the beam could be bimetallic layer. Okay, other than bonding the material of 2 different thermal expansion coefficients to generate bending, it is also possible to create a displacement with the bending of V-shaped beam. So you have a 2 segment. If you have thermal expansions in both legs of the V segment, then you're going to have the apex motion at the tip. Likewise, if you are connecting a long beam with a short beam, and when you do the heating up, because of the difference in thermal expansions, then you're also possible to generate the bending. And last, you can also introduce bending by introducing a passive segment. Heating happens at the short segment here and the long segment here. The cold arm, which is wider, are not expanding or not heating as much. Okay, how to model the beam bending? Okay, and if you are using the V-shaped beam as an example, okay, let's see. This is still about the application. You can see this kind of main structure. Okay, it's built on top of the wafer. So you are making a very tiny beam. Okay, when you doing the heating up, this V-shaped beam will do the deformation. Okay, when you heat it up, then it will expand. Okay. So how this expansion is going to be modeled? If you model them as a rigid body, our linkages. So this is what you're going to have. 所以看到没有？如果我把这个梁模拟成这个杆，它这个杆的伸长，那很容易就用这个 来计算，但这个毕竟是没有边界没有约束的感 ，OK。This is a pin supported linkage which has the thermal expansion. So you can model this to find out what is the vertex the displacement. But in reality, beam is more than linkages because beam can resist bending. How are we going to model this beam bending? We have a very simple idea about beam bending. How do you model beam bending? You model it as a circular arc. Assume you have a prismatic bar. If you try to bend it into circular arc, one geometry you notice is you will form concentric circle. 我们来看一下，你要怎么模拟你的引量？我们就拿这一小块。Okay, if you have this of length L, okay, if you now doing the bending, okay, you going to form two surface. This is the top surface. Okay, if you're going to model it, you find this top surface, okay, is lesser than the starting length. This is the top, and then you look at the arc length here. Okay, this is going to be the bottom. It's going to be greater than your starting length. So you can see that there is a strength difference. Okay. So this is the finally derived formula relating the radius of curvature. How do you define radius of curvature? This is the radius of the circular arc at the neutral plane. Okay. Okay. So in a way, if you learn Hooke's law, okay, this is a spring. If you're doing the pull, then you see this pulling force will result in the elongation. So this is the Hooke's law you learned about. But what about the beam bending? This is a starting beam. Okay, if you are doing the flexing, so that it forms the circular arc, okay, then the radius of curvature is what you measure the moment. Okay， 有同学看到没有？你如果单纯是悬臂梁，单纯是这个弹簧，你有5个定律，但是对于梁而言，你如果施加的是一个纯扭矩，那扭矩造成什么？扭矩造成这个横条从一条直线或者直条会变成了一个同心圆，这个同心圆的这个半径就是你的曲率半径，那你的 moment 越大，你的曲率半径就越小 ，OK， 所以它这个 moment 呢是跟你的曲率半径的导数成正比 ，OK。And how about the stress? And then the stress we obtain is related to the moment as well as the height. Okay, further away from the neutral plane, higher the stress. At the neutral plane, zero stress because we have imposed a condition. In this case, we are doing the pure bending. Okay, there are no elongation at the neutral axis. Okay, so pure bending will cause this to form a circular arc. Okay, the top surface and the bottom surface being concentric. 所以我们在模拟这个纯关系的时候，你可以把横条模拟成是一个弯曲的这个几何，它这个上面这个面变成跟外面这个面，下面这个面成为同心圆弧。Okay, and then how much is the elongation? Okay, if the neutral axis remains the same stopping length as the straight beam, so the inner side of this concentric circular arc will then have the reduction in the length. Okay, this circular arc has an arc length of r d theta. Okay, and now, okay, how much is this arc length? You can describe it using the dy dx. Okay. This is log. Depends what you want to write. Okay. In this case, we are writing this. This arc length can be difference in positions, and the diffraction is dV. So the arc length is obtained as the hypotenuse for this right angle triangle. So you can make use of the Pythagoras theorem to find out the arc length. Dx is equal to dx times the square root of 1 plus the square of dV dx. Okay. So next, then how much is the deflected angle? If you look at this angle again, this deflected angle is nothing but dV dx. Okay, it's using the tangent of your this right angle triangle. dV over dx is equal to the angle theta. And then if you combine it, okay, if you do the partial differentiation of this deflected angle, then you're going to obtain the change of the angle is equal to the second order derivative of the displacement times the dx. Okay? And now, if you take this change of the angle, okay, times the radius is equal to ds. So using this relationship, 1 over the radius of curvature is equal to the change of the angle versus the change of length. If you do the substitutions, then you finally get your radius of curvature. Okay. So this is a revision of the mechanics of material. Okay, and next we'll come to the point. So what makes beam different from a stack of paper or stack of layer? So a beam has 2 layers fused together. If they are not fused when subjected to bending, you can see the layer don't change in length. They can be subjected to interfacial sliding. Okay? So but now if you make them together, okay, it is becoming stronger and it can withstand greater loading. Okay? So what is the strength distribution along the layer of beam? Okay, to take this for example. We tell you already, one segment of the beam, it was initially straight. When you bend it, okay, you form concentric circular arc. Okay, the one on the top, A prime, B prime, is become shorter. Shorter by how much? Okay, the neutral axis has fixed length equal to AB. Okay, it doesn't change. This, when they form, this neutral plane remain the same length, which is r with theta. Okay, however, the top surface is going to shorten. Why is it going to be shortened? Because it has a smaller radius than r. How small it is? It is r minus y. This is the radius r. If you leave up by height y, this is going to reduce the radius. If you multiply the same angle, then you got your top arc length. Okay, this top arc length is shorter than the starting arc length r with theta. So in the end, you have the minus height divided by the radius of curvature. So as a result, if you now have the strength and you multiply it with the Young modulus, you're going to get the stress. And this stress, okay, this stress is internal stress. It's going to be balanced by the external moment. And this external moment minus the stress times the area. Okay, stress times the area times the height. 那我们来看一下这个图。这个后面是会用，这东西如果说有兴趣的话，可以自己去复习一下。OK， 看到没有？如果你把它取成一个面。OK， 把一个长条的取成一个面，然后你这个是一个转弯半径。This is the neutral plane or neutral axis. OK， 这样的量还是有一个假设的这种。你在纯弯曲的时候，它长度不变，因为我没有感受到一个静拉力。OK， 但是上面这个面，上面这个面。它离你的这个不伸长面有一个高度 y， 那你如果发现你要 draw， this is a concentric circle. If this is r, this angle is d theta. This is r d theta. Okay. How about this arc length here? The arc length here is r minus 1 d theta. So, if you are not subjected to a perfect bonding, they should remain the same length. But now, this is shortened. Shortened by how much? The chain of the length is equal to r minus 1 d theta minus r d theta. Let's change the color. So in the end, your change in the length is minus 1 d theta. Okay? Is it? And if you divide the starting length, okay, we're going to obtain the strength. Okay? So you can see that the strength on the top surface here, which is, the strength here is the L over L is equal to minus Y over R. Okay? As a result, you're going to have, if something is bending you with the moment so that you become a laughing beam, internally you're going to have the opposing stress. Okay? Your stress is actually forward. Okay? It is your negative E epsilon. Okay? I'll just take the sign. So this is your Y over R E. Okay? It's the stress opposing this. 所以就像5个定律，你拉弹簧的时候，弹簧拉长了，请问你的内应力是沿着长度方向还是跟长度方向相反 ？OK， 你拉长弹簧，那长度伸长是正的，但是你的弹簧力是跟伸长方向相反。 所以你的这个我讲的这个内应力是反向的。OK， 那现在你的内应力，所以内应力你又可以把它写成什么 ？If now look at the beam, okay, this beam have a layer like this, so you can write the force equal to the stretch times if the width is the let's say anyway this is the A. Okay, that's one. So this is now the force. You can see this is force dF acting above the height y. Okay, and then what's the moment? Your counter moment, okay, above the neutral plane is dN is equal to y dN. It is equal to y sigma dN. If you do the substitution here, then it is equal to y squared over r times e dA. Okay. So eventually, if you now do the integration from the top strip, top layer all the way to the bottom layer, from y equal to top to y equal to bottom, then you finally going to obtain the moment is equal to the Young modulus times this second moment of inertia, the second moment of the cross-section area divided by the radius. Why is that the case? Because if you do the integration here, this is equal to I. Okay? So this is equal to EI over R. 所以我们就找到刚才的这个公式。So now we come back to the summary. So your moment is proportional to the curvature, which is the inverse of the radius of curvature. Okay? Of course, if you want to look for the stress, you can do the substitution in. You can find out what is the top stress. Yeah, the stress level is M1 over I. Okay. 你们记公式的话，大概只要记这两个，那些中间项就好。This is the primary formula. Okay, this is the second one. Okay, so let's revisit the mechanics of material again. So remember that when you are trying to solve for the beam bending, you are writing the moment balance and force balance. So in this case, a general beam will be subjected to distributed force. Okay, this is what you have derived before. Okay, but in the finite element, we're going to do the simplification. We will not consider distributed loading. We will only consider the shear loading at the two ends. Okay? So how this simplification is possible? Let's look at the example. Let's take one segment of the general beam bending. So it is subjected to shear. The shear force on the left hand side is downward positive. The shear force on the right hand side is upward positive. The moment and the right hand side is counterclockwise positive, and then the moment is the clockwise positive. This is convention of mechanics of materials. And then in this case, the distributed force is upward positive. Okay? So with this, now we can write the force balance of this beam segment. Okay? This for this beam segment, the total vertical force is going to be balanced. Meaning the right hand shear force upward minus the left hand downward shear force plus the upward distributed force is sum up to be 0. Okay? So this gives you the calculation that the change in the shear force between the right hand side and the left hand side is going to be opposite to the upward distributed force. Okay? Next, we are doing the moment balance at the right hand side at the center point O. If you do this moment sum, okay, and let's say you do this clockwise one, depend what you like. If you want to do counterclockwise, also can. If you do clockwise, you're going to eventually write the same thing. Let's say you do the clockwise one, in the case of clockwise one, you have the left side moment plus the left side shear force induced moment minus the distributed force induced moment, and then minus the right hand side moment. So after the simplifications, you can find a common end, which is positive and negative, are cancelled out. The common, and then the next thing is we negate the higher order term. The dx is higher order, we negate it. And second, the x squared also higher order, you neglect them. So in the end, you find that the change in the moment between the left hand side and the right hand side is depending on the shear force of the left hand side. Okay? And now, we can do some practice to find out, okay, how the shear force is determined. Take a cantilever for example. If you apply the force at the tip, if you want to find the moment, you have to determine where are you standing to get the moment. Okay? If you are taking from the free end 0 moment, and then you make a cut and you stand the edge close to the free end, then you can see the counter moment at the point of the cut is going to oppose the tip force. However, if you now look at the inner side of the beam, this cut, which was having a counterclockwise moment on the right free end, is now becoming is it counterclockwise? I think you've got to do the opposing. Okay? So if you're now doing the beam bending, you're still going to induce the same beam bending, but the left hand side and right hand side, you got to change the direction. Okay? So finally, we come to the beam element. 所以看到没有？我们现在给你看到的是你材料力学上的量的分析。就是材料力学相对而言比较精准的，因为它可以分析你的分布率 ，OK， 它可以分析你的这个叫什么剪切率都没问题。但是来到有限元素 ，OK， 我们做了什么一个重大的改变？我们重大改变就是我这个量元素不承载分布率，它只承载剪切率 ，OK。So how do you make this simplification? These simplifications will only take care of the end displacement, which is the vertical deflection on the left hand side and vertical deflection on the right hand side. Okay? Whether the beam is smiling and not smiling or upside down depends on the angle. Okay, the angle theta 1 and theta 2. 那你一般材料力学，你可以说这个微笑的你，我们拿这个微笑的你。Okay, if you take this as a beam, you say this is a positive bending. When you say positive bending, okay, your right hand side, or my right hand side, the left hand side, will induce a counterclockwise bending, and then my left hand side. The right hand side would induce a clockwise bending. So this is convention of the beam bending. 所以你在传统材料力学量分析的时候，你的右手的 moment 跟左手的 moment， 一个是逆时钟是正，一个是顺时钟是正。OK， 这是你一般的做法。
但是我们现在来到有限元件分析的时候，电脑不分你左右 ，OK， 听懂吗？我的左可能是你的右，我的右可能是你的左，所以我们现在做有限元分析都很简单，不管你是量元素的右手边还是左手边，我们定义的量元素的转动一律逆时钟离正，这边是逆时钟离正，这边这个左手边也是逆时钟离正。So in this case, you are defining the angle of diffraction to be positive counterclockwise. Okay. So how about the vertical displacement? Okay. For the case of vertical displacement, so you're going to have upward positive. Okay. So this assumption is true. Okay. Yeah. No matter how the bending is, if it's going to be downward, then this displacement is going to be negative. Okay. Okay. So using this, we are still applying the mechanics of material. Moment is EI over R. And what is your R? It is the second order derivative of the vertical diffraction. Okay, times EI. Okay, so M is equal to EI, second order differentiation of the vertical diffractions over the space. And then what is your shear? Remember, your shear is the N dx as we obtain from your mechanics of material. Then in the end, it's going to be EI times third order derivative of the vertical diffraction. And then lastly, if you do one more kind of differentiations, okay, you're going to obtain the distributed force equal to fourth order of the vertical diffractions. Fourth order derivative of vertical displacement times EI. 所以这个是我们用的一个假设。OK， 那我们还最终多了一个假设。不好意思，我不分析分布力，所以我这个4次元的这个我这个第4次的微分等于0。Okay, if this is true, then you can start doing the integration. Okay. So you learn that M is EI, second order derivative. 同学这个应该记得吧？是你大二的财力，整个学期或者上个学期就一直在解这题嘛，对不对？而且有很多变化。那我现在 V 是 EM dx， 那就是 EI 这个 V 的30微，那你的 Q 是比dx， 那就是 EI 这个垂直力的4次微分。那我们现在有限做了什么事？我们做了一个解法 ，Q 等于，所以这个 EI 40块。啊，如果这真的是0，那我们现在就可以开始做微分了，做积分。所以 this is true. What shall we do? Okay, this is V fourth order derivative of V is equal to 0. Then the third order will then be equal to, let's say, A1. And then second order, we have A1x plus A2. Then, how about the first order derivative? It is a1x squared divided by 2 plus a2x plus a3. And then finally, your b is equal to a1x 3 divided by 6 plus a2x squared divided by 2 plus a3x plus a4. OK， 好，解完这个，那我们后面要解什么？它这个 solve for the expressions for the vertical displacement. Eventually, you're going to solve for the unknown coefficient a1 and a2.边界值问题，所以你要带入的是一个边界值，那你就可以做一个近似。Okay? So what you are solving is the boundary value problem. Okay? So if you're going to solve for A1, A2, and A3, A4, you're going to apply the boundary. What is the boundary? Your unknown is B2, beta 2, B1, beta 1. But you are now treating your boundary unknown as the norm. Okay? Your theta is changing over space. Your B is changing over space. But now you are saying at x equal to 0, b x equal to 0 is b1. Beta x equal to 0 is beta 1. And then at x equal to L, your bx equal to L is equal to b2. Your beta x equal to L is equal to 2. 你把这些边界都带进去。And then what is your theta? Your theta is dv dt, dv dx. Okay? So this is good. Why is good? Because you are going to make use of this information to help you finding the coefficient. So we're going to do the substitution here. 好，那我们就开始来解。那你第一步要解的是什么？我先盖住。我先解这个左手边。Okay, let's see the top one. Okay, I first now going to substitute the boundary on my left hand side. Okay, 如果你忘记了，看这张图，这个左手边的这个边线图，位是 B1， 角度是θ1，一个向上，一个逆时。Okay, 这是第一个边界。这边界好找。When x is equal to 0, when x is equal to 0, these three terms all going to 0. So your A4 is equal to B1. Okay, and then when x equal to 0, these two terms are all going to be 0. Your A3 is equal to θ1. Okay, so in this way, you got the A3 is equal to θ1, your A4 is equal to B1. Okay? After that, what do? You do the substitution. Okay, what are we going to substitute next? We're going to substitute the second boundary condition. On the second boundary condition, at x equal to L, my B is equal to B2, my angle is equal to theta 2. Okay? By doing this, okay, B at x equal to L is equal to A1 L cubed plus A2 L squared plus A3 L plus theta 4. If you substitute what you know about A3 and A4, then you will have the expression simplified with two unknowns. The only two unknowns are A1 and A2. A3 are A4 or solved. Okay, and then next, you can make use of the gradient of the vertical diffractions to find the angle. Angle of diffraction is 3A1 L squared plus 2A2 L plus theta 1. Okay? So what are the unknown? 我们来画一下哪一个是未知数。我们把未知数画成红色。开始都很多例子，那到后面你就只剩下两个例子。So with this, you finally solve and find what is your expression here. Okay. Now let's do this solution. In the end, you are left with only two unknowns. How do we solve for your unknown? Okay, we do the solution by Cramer's rule. Okay, anyway, you can solve all these funny things. Okay? But I think you shall do solution by Cramer's rule. Okay? Do Cramer's rule 的解法。中间那个你们要怎么？高斯相似法则去做，那我们现在就用这个Cramer's rule。Okay, so in the end, we solve for your A1, A2 as for this expression. Okay, you are not sure? Yeah. So A1, A2 are the unknown. Okay. To avoid the confuse, I try to make them different colors. So I make this as a boundary. Let's make it blue. This is the boundary that you apply. You then tentatively assume them to be something to be expressed. 所以这些都一律变成是边界。这边界虽然是最终要找的一个意思，但是我们暂且把它暂定为是一个已知的。那我们先解决这个叫形状函数。那这些一律都是这个叫边界，我画蓝色。These are the boundary values, either 0 order or the first order. What was your unknown just now? My unknown was this A1, A2. The unknown to be solved.所以你就知道你的这个矩阵法的这个好处了，因为矩阵法可以帮你解这个每地方解得很快，而且哪一个是未知，哪一个是已知的都清楚。不存在这个模糊地带。After you have do the coefficient determination, okay, what do you have? You substitute all the variables A1, A2, A3, A4 into the expressions. You eventually manage to find D equal to the sum of a few terms. Okay? 所以我们第一个式子写的是什么？第一个式子写的是你的位移是空间分布。你如果忘记这个是怎样的一个叙述？我把这个图拉上来。放在上面。OK， 你的位移是空间分布。但它这个分布是什么样子？答案很简单。OK， 你拿一张纸。OK， What is the shape of the displacement distribution？ 好，我们本着那个叫做差分法的原理，你觉得你第一个这个空间分布的这个位移？ OK， 比如说我右手边向上抬高一个单位，这个函数它就应该长得跟这张纸的形状一样。那如果左手边其他都不动， 我左手边向上抬一个单位，它就长了这幅模样。对，第四个情况，我右手边扭一个角度，它就长了这个形状。我左手边扭一个角度，它就应该长了这个形状。Okay? So the polynomial here is a function of space. Okay, let me write this. Okay. The polynomial function b is equal to coefficient a1 x cubed plus a2 x squared plus a3x plus a4. You know these are v1, v2, v1, v2, v1, v1. But the coefficient here, this is more complex function of theta 1, v1, theta 2, v2, x. Yeah, the different function. Okay. This writing concerns about the shape change over the length. Okay. 这是我们一开始解的题目，我们这个叫 x 的 polynomial。但是我们不要忘记，我们最关键的是边界值。What we care most is not the shape function. What we care most is the solution of boundary value. Even though we take this temporary as the norm value, but eventually what we care most is still how to solve this unknown value. So how are we going to arrange this d? We're going to arrange this as a function that is depending on d1, a function that is depending on theta 1, a function that is depending on d2, and then a function that is depending on theta 2. These functions are functions of x. These are functions of x as well. These are functions of x as well. And this is function of x as well. But their shape are different. 好，看到没有？我们的式子展开，长得这副模样。第一个是 n1， 第二个是 n2， 第三个是 n3， 第四个是 n4。So after getting this, yeah, this is the grouping of my expression. In my grouping, I got theta 1 in blue color, theta 2 in black color, v1 in red, and then v2 in pink. And now I do the grouping. v1 is multiplied with shape function 1, theta 1 is multiplied with shape function 2, v2 is multiplied with shape function 3, and theta 2 is multiplied with shape function 4. Okay. Now the important thing is the plotting of the shape function. How can you express this? Okay, this shape function is a space function of function of space. And then you multiply it with the boundary, you want theta 1, v2, theta 2, then you should solve for that. 我们来看一下这个式子怎么画。这式子还真的跟我刚才叙述的这个一模一样。拿一张纸，或者拿一把尺，右手边定义 v1， 定义转角 ，OK， 左手边也定义垂直位移，那垂直还有转角。那我们先看这个是这个 n1，OK，n1 跟 n3，n1 跟 n3 叙述的什么？垂直位移的形状函数。What this describe? The blue color one is describing N1 displacement and the shape function. Previously, you know the shape function for linkages is just a linear slope. Okay? But here, for a beam bending, the shape function, if you now apply only 1 unit of vertical displacement, other displacements are all 0. You do not leave out the right hand side. This S-shaped curve is shape function N1. Okay? And then next, you do the same for the right hand node. If you leave out your right hand side by 1 unit, all other equilibrium fixed. Even the rotational angle fixed to be 0. Then this is the second shape function. 来张纸自己移一下，这个形状函数就完全符合你的辨识。And then next, we are talking about the same piece of paper. Okay, but rotation. The rotation of left hand side to be 1 radian. Okay, I did not do any translation. I only do right hand side rotation by 1 radian. What is 1 radian? 3.14 radian is 1 pi, about 180 degrees. 1 radian about 1/3. So it's close to the 60 degrees. So this 60 degree counterclockwise rotation will bend the beam like this without any vertical displacement. Okay? If you do the same on the right hand side, okay, you should do the flexing. Okay, this one I need to flip the other side. It's not negative, right? This one flip the other side. Okay, 1 unit. With this, we know the interpolation function for displacement. Okay? Yeah. Okay. 所以这边有一个那个负值，它有点应该说是照顾到你左右边要平衡的关系。为什么？你如果定义这个是 sprawling 这个 moment， 它左右 moment 一定要反向，所以你才会有一个这个是一个正的45度，一个是负的45度。So with this, then we'll be able to obtain the profile. Okay. Okay. So up to now, we get the right shape of vertical displacement. If you do 1 time differentiation, you got the angle of diffraction. If you do it 2 times differentiation, you got the shear force. Okay. So recall the formula here. Okay. 1 time differentiation gives you the angle. Second time differentiation gives you the moment. Third time differentiation gives you the shear force. This is what you previously defined. After obtaining the expression of shape function, you can do the differentiation 1 time, 2 times, and 3 times. Okay? So this is the final expression. Okay. 0 order differentiation, 1 order differentiation, 2nd order, 3rd order. And now, okay, important thing come here. Okay. For 2nd order differentiation, you know second order differentiation of vertical displacement is giving you the moment. Okay? But here, okay, how do you define the moment? Okay? The moment here, okay, unlike the conventional moment definition. Conventional moment definition is counterclockwise positive on the right hand side and clockwise one on the left hand side. Okay? Do you need to take care of this? Yes, you need. But you take care by the sign. 所以你看到我们刚才的形状函数吗？这个形状函数。它给你看到的，我们拿角度，这个正与负 ，OK， 它照顾的是什么？你微分完过后，它照顾的就是一左一右的 moment 正负号，它要互相平衡。But in the expression, what do you see? In the expressions, you have because now we take counterclockwise angle positive on the right hand side and on the left hand side. If you do partial differentiation twice, okay, if you take this convention, if the shape functions are all positive, you will not get the moment balance on the left hand side and right hand side. But because of the shape function has taken care of the sign convention, so you see the right hand moment, it is clockwise. But if I stick to the moment to be negative, to be positive clockwise, then this counterclockwise moment will be negative. 那事实可能可以去看 ，OK， 它有点复杂，但是我们讲的是它的物理。Then, so in this case, you see here, it is tally with the convention of your maximum period. Okay? Even though I define all the angular deflection to be counterclockwise positive, but the moment part has to be taken care because of the shape function. Okay? And then, 那垂直力的部分呢？那垂直力的部分就还好，我们看垂直力，你的剪切力是怎么定义出来的？你的剪切力 ，OK， 看一下我们这个剪切力，你看到我们的剪切力吗？If you look at the shear force on the beam, on the left hand side, the convention tells you it is upward positive. On the right hand side, the convention tells you it is downward positive. But because in my definition of the vertical displacement, it is both positive. Okay? How do I tally with the convention of your mechanics of material? Or how do I tally such that the force balance is zero or nearly zero? Okay? 来，同学，为什么这边左边的剪切力跟右边的剪切力合起来要等于0？可以等于0吗？我问一下同学。来，这个抄写的没有讲过。左边的剪切力跟右边剪切力加起来可以不等于0吗？不可以对。为什么不等于？前面可以不等于0吗？不等于，然后有一个如果是考材料力学，可以不等于。 但是好有限，那和谐要平衡。So in the case of quantum mechanics, yes, left hand side and right hand side shear force sum can be non-zero because of the distributed force. But look at the finite element. What is the assumption of the finite element? The finite element assumes no distributed force. So the right hand shear force and left hand shear force is going to be zero. OK? 这是你在推这个有限元素的时候的一个假设。那你是靠元素数来取得准确性，个别单元这个不准，但是你现在可以用很多元素。So in this case, what is the vertical shear force? I define it upward positive in my convention of mechanics of material on the left hand side. I define it downward positive in my convention as well. But now look at your vertical displacement, both are positive. So when you do the partial demonstrations, good thing here is F1 obtained from third order partial differentiation of V is giving me a positive value because they are tally in direction. Vertical shear force and vertical displacement are tally. Okay? But on the right hand side, V2, the vertical displacement is defined positive upward. But my shear force is downward positive. Okay? So here you can see F2 is negative here. Okay? So with this, what I obtain can fully be confirmed to be right in convention. OK， 好，那我们刚才解的这个 moment， 它是垂直位移的二次方向。那我的剪切力，它是垂直位移的三次方微分项。OK，I have now obtained the expression. How do I turn it into finite element? Okay, there are supposed to be 4 equations. The left hand side of 4 equations are force and moment, not 1 and not 2. The right hand side of the expression are angle and displacement dependent. What I'm going to do is, my left hand side is what you call moment vector or force vector. Force, moment vector, they are all external force. Okay? Right hand side is the stiffness times the northern displacement vector. So the right hand side is my internal force. So to read the equation, it is external force is balanced with the internal force. Okay? So take the first equation as for example is going to be EIL cubed times 12V1 plus 6L theta 1 minus 12V2 plus 6L theta 2. If you continue this substitution, you're going to obtain the shear force moment vector is equal to EIL cubed times this matrix. The whole thing, including the coefficient, is what you call stiffness matrix. And then the right hand side is the vector. This is a northern displacement vector. This displacement including both the vertical and the angular displacement. 那我们大概顺便要把这个画弧给展开来，为什么？因为这个是包括你的这个系数，你要乘上这个系数，整体才叫这个刚度矩阵。这个刚度不是线性的刚度，它也是这个弯曲的刚度。Okay, and then finally, let's come to the example. Okay, you have solved it by this beam bending theory, isn't it? Can I use what I derived to find out the vertical deflections of this simple cantilever beam? This is a single beam element. Okay, The left hand side is fixed, so the vertical displacement is 0, the angular displacement also 0. Right hand side is subjected to a shear force coming down. Okay? So your V2 is minus F. But the right hand side of this cantilever is subjected to no moment, so they are 0. So if you now using what we have obtained as the beam element, left hand side is the force moment vector. You can see left hand side is fixed, so that they got the shear force, reaction force. They also got the reaction moment. And then the right hand side, the dot 2 is subjected to downward force, 0 moment. And then it's equal to the status matrix and displacement, either transverse or angular displacement vector. And then here, because left hand side is fixed, V1 is 0, theta 1 is 0. So in the end, you're only left with this small matrix to be solved. This small matrix has the force vector minus F 0, 0 moment is equal to L over L cubed times the 2x2 simple matrix. This is 12 minus 6L minus 6L 4L squared. 在解题的时候，顺便可以做一个检查。如果说你的矩阵本来就是从既有的刚度矩阵取下来，你的矩阵有这个斜对角对称性，所以你的斜对角是对称的，是一样的。那你如果觉得好像不对了 ，OK， 你还没加入边界条件哦，这个时候你要检查一下是不是你抄错。Okay, with this, now we do the solution. So this is a 2x2 matrix. You can do Gaussian eliminations, but if it's 2x2, I'm more than happy to apply my reference rule. So to solve for unknown V2, theta 2, let's say V2, I can find V2 is equal to F over 3EI over L cubed. So in this case, it tally with my solution. Likewise, you can obtain the tip angular deflections. This is FL squared over 2EI. It is the negative. Negative sign means that it's not counterclockwise, it's clockwise. So you should know that under the vertical tip loading, the displacement is negative, and then the angle of deflections is also negative. OK， 好，那我们现在就休息15分钟，等一下再继续解题。